we're going to be diving into the quantum formalism part of the introduction. And yes, I know I've skipped all the previous chapters, and so just, diving right into the quantum stuff. Let's see where this takes me. And I am aware that at some point I'll have to actually take a look at a more hands-on stuff and actually take a look at some of the tooling, which I'm actually quite looking forward to do that. But I feel like I want to do a bit of a kind of like steal like a bird's eye view on the whole quantum stuff, right? So we've got quantum formalism, quantum measurement, operators. It's going to be interesting. Wave particle duality, uncertainty relationships, relations, correspondence with relativity and quantum mechanics. Okay, so this is really where. Okay, so that's really these sections, right? So there's not a lot to it. Um, I mean, probably those are a bit bigger and probably denser, but yeah, let's see. I first want to just go through this stuff and kind of like, peel that off layer by layer. And yeah, I don't know, it's a bit late to be honest here. It's like it took me a bit longer to get started, but um, so I might not stay up long. Um, who knows? So let me see. Is that everything here well set up? It says that I'm live. And what about I just share the stuff quickly in Twitter? Anyone wants to join to watch the learning session? Maybe learn together. Come join me. At Twitch TV/uncertainties. There you go. There you go. Anyway, so to continue understanding how our models might relate to quantum mechanics, it is useful to describe a little more of the potential correspondence with standard quantum formalism. We consider, which we don't know, right? So I'm totally like, so I've done the, kind of spent quite some time going through the quantum computing stuff, and therefore some of the quantum basics are there, but like the full quantum formalism is something that I haven't really explored, and that's kind of the whole purpose of these, right? We went last time through the basic concepts of quantum mechanics, and I think that I grasped at least what's the basic idea. And in that, I first thought that, and actually it's maybe good to recap a little bit, right? But I first thought that this is like, this is sort of this multi-way evolution where I kind of thought like, yeah, well, that's kind of like all the possible actions you're taking, but then I couldn't really understand much. Like, is it that A and B are qubits or whatnot? And then, if I remember well, yeah, these stripes, these lines in here are kind of splitting the time steps, so they're kind of like the moments in the circuit, so to say. And then there's something like conversions. This red states in here is something like, yeah, like if it's sort of if if you are at AA, like you can evolve to you're going to evolve to ABAB regardless, um, right? Regardless of that's going to be a valid state regardless, because these steps will just indicate you the possible applications of the updating rules, and this is like at the end of the day what happens if you would apply both rules, right? Something like these, which I kind of felt there was a bit of an analogy towards like what happens in a moment when you actually apply like a Hadamard gate to a qubit, but then to another qubit, right? Like if you're just thinking about the execution of a circuit and you just think about the first Hadamard being applied, but not the second one, then you're in one of these non-red states. But then when you have both applied, then you're in one of these red states. But I'll probably have to, reread that anyway. So, but let's go ahead with the quantum formalism. So consider quite directly each state in the multi-way system as some quantum basis state S. Okay, so that is actually okay. That actually makes it easy to understand. This means that each of these things is a basis state. But that's interesting because so what this will mean is that actually, if I just take a look at that snapshot here, like, of course I start just with one basis state because that's probably the zero state, so to say, right? Um, and then it kind of evolves because it seems like you'd be growing the amount of subsystems and qubits because you're going to have like in each of these. If I were to cut these the way they did that in the previous section, I kind of have 1, 2, 3, 4, 5, 6, 7, 8. So that's like 3 qubits, right? So it's 8 basis states. Yeah, it's 2 to the power 3. But of course it can go on, right? So I don't really... An important feature of quantum states is the phenomenon of entanglement, which is effectively a phenomenon of connection or correlation between states. See, that is actually something that I saw a while back, and it confused me, right? Because is it that it's a correlation between states, or it's a correlation between systems? Like if I have 2 qubits and they're entangled, like all together they have an entangled state. The way that I see it is it's easier to think about the qubits being, the things being entangled rather than the states. Like if I have a Bell state 000011, I would say it's not that the 00 and the 11 states are entangled, right? It's rather than the 2 qubits are entangled. Remember, so if I have like a 00 plus 11, right? And this is like, yeah, whatever, you've got this coefficient in here, right? And the thing is, you can't really tear these things apart into a product of 2 separate qubit states. And so you're saying that Q0 and Q1 are entangled. Basically, yeah, there's no way you can separate the states. But I'd never say the state, because these are basis states, right? The 00 is a basis state, the 11 is a basis state of like 2 qubit systems. I would never say these states are entangled. That's what's confusing me a bit in terms of, and I remember seeing that and asking that in Twitter even. But anyway, in our setup, as we will see more formally soon, entanglement is basically a reflection of common ancestry of states in the multi-way graph. Okay, so this means, and I've heard, and again, I've watched some of the videos. I used to do that, and I should probably, I'm kind of trying to think about a format to do that as part of the series as well, to watch some of the working sessions about quantum mechanics and try to kind of watch them and comment live as I watch. Because they did mention that a while ago, if I remember well, but that would be confusing, right? Because then it means that these two basis states are entangled because they have the same parent. And interference can be seen as a reflection of merging and therefore common successors in the multi-way graph. So that would be interference, like, well, in a way, yes, right? Like, for example, going from AA to ABA and ABB to ABA, right? Because if you think about the way this happens is they both lead to the same state, and so they interfere. It's almost like saying, if I am, and I might be getting this totally wrong, right? But let's see, that's the point of learning here. So let's say that we have the states 0, 0, and 1, 1, right? And they are entangled. But it's funny because they'd be entangled, I don't know. Yeah, their parent is the 0 plus state, is it? Because that's what the state before being entangled. That's kind of, that's also not true because we're applying a control knot. Yeah, okay, so control knot could lead to this state or could lead to this state. I guess that's what it's saying. Because the replacement rules of the control knot, God, my writing is awful here. Let's get better at this. The replacement rules, and I like how this is really connecting to what I'm to the other work that I'm kind of finishing up on the in the Python library. The replacement rules for the C naught would be of like of 2 gates, right? Would be like take the 0, 0 state into 0, 0 state, right? The 0, 1 state into the 1, 1 state, the 1-0 state into the 1-0 state and the 1-1 state into the 0-1 state, assuming that's the controlled qubit. And at the end of the day, this parent state is nothing else than the 0, 0 plus 1, and so the 0, 0 plus 0, 1. And so you can apply to rules. So you have a set of rules, right? And so, but the result after applying all the rules, all the possible rules, is really, you know, that is rule number 1 turns into 0, 0. That is rule number 2 turns into 1, 1. Okay, but they're not two separate states. They're still one state. So these would still be in this multi-way stuff. I'm getting a bit confused because this is getting a bit confused because I don't know. This should be separate nodes in the multigraph way, but like I can't really. It feels like it's somewhat connected to this, but I'm not managing to make the full connection yet. I'll get there, I guess. Kind of mapping this to zeros and ones, right? So yeah, I guess Q study. I guess you're Victoria, based on your comments in the language. Yeah, it's a bit late. Sorry for that. It was a long day, and I just felt like I had to. Though it was a busy day. It was actually a bothering day, and I kind of yeah. I felt like that was a necessary thing to finish the day to some extent. So um, each pair of states generated by a branching, each pair of states generated by a branching pair of states. Yeah, but some branches generate 3 states, right? But each pair of states generated by a branching in this graph are considered to be entangled. And when the graph is viewed as defining a rewrite system, these pairs of states can also be said to form a branch pair. Given a particular foliation of the multi-way graph, we can now capture the entanglement of states in each slice of the foliation by forming a branchial graph in which we connect the states in each branch pair. For the string substitution system, both the sequence of branchial graphs is then. Okay. So, so these are just the foliations, right? And by foliation, I mean if you just cut things through, I think that's what they call foliations. So each pair of states is entangled. When the graph is viewed as defining a rewrite system, these pairs of states can also be said to form a branch pair. So that will be a branch pair, that will be another branch group, I would say, each right going on like this. Okay, but all connected to all. Okay, so each pair on the foliation is entangled. Right? That's the AAA. Yeah, that's this foliation. And AAA. Oh, but look at these. AAA is only okay. No, it's not that each with each of them, but it's like only their siblings, like actual real siblings, right? So with ABBA and AABB and ABAB with 3, AABB, ABAB, ABB. Why? Oh, yeah, of course, because they also share these one. Okay, I get it. Yeah, so they share ABA. Okay, I get it. In physical terms, the nodes of the branchial graph are quantum. The nodes of the branchial graph are quantum states. Quantum states are quantum basis states, and then the graph itself forms a kind of map. In physical terms, the nodes of the branchial graph are quantum states, and the graph itself forms a kind of map of entanglements between states. In general terms, we expect states that are closer on the branchial graph to be more correlated and have more entanglement than ones farther away. So that would be an interesting concept of measure of entanglement. But if each node is a state, I just don't get how I guess that is just an example, which is, but maybe I'm just trying to map the wrong thing. Maybe there's just no way that you can evolve it like that in a quantum circuit way, where it's like you take these to these state. Each It is also not true, right? That is also weird, a bit confusing, because if we're talking about the same system that's evolving, like how can I map these nodes to basis states? Like I like what's it means that A should also be included somewhere here. If I say that's a basis state that I start with, and then I evolve the whole thing, that's still really confusing. So I kind of half get what they mean, but I'm not so sure if it all fits together. So, but okay, let's say each foliation represents each node a pure quantum state. No, each node a pure quantum state, or yeah, each node a pure quantum state, right? But again, then states are not just entangled, like that's confusing. States entangled. Like when we say entangled states, we mean that a full state is entangled. And what this seems to indicate is that each of the nodes is an actual it's a potential state of the system. Because this seems to lead to the fact that counting the paths down here, and I remember hearing this in one of the videos as well, is also is something that you could then use to kind of calculate the coefficients, the complex coefficients, or the probabilities, maybe not the probabilities of observing that specific state. So these are, I mean, and again, let's stick to these, right? So these are really quantum basis states, like each state in the multi-way system. It's a quantum basis state. Okay. As we discussed in 5.17, the geometry of branchial space is not expected to be like the geometry of ordinary space. For example, it will not typically correspond to a finite dimensional manifold. You know what? Like I keep seeing manifold, and I really have never checked what it actually means. What is a manifold? Is it just a surface idea? Yeah, I think in mathematics, manifold is a topological space that locally resembles Euclidean space near each point, more precisely an n-dimensional manifold, or an n-manifold for short. It's a topological space with the property that each point has a neighborhood that is homeomorphic to the Euclidean space of dimension. Oh God, why do you make definitions so complicated? In a nutshell, it's just a surface, right? A topological space is a geometrical space in which closeness is defined, but generally cannot be measured by a numeric distance. More specifically, a topological space is a set of points, along with a set of neighborhoods for each point, satisfying a set of axioms. Yes, it's just okay. So it's like a surface, right? Or it's like a space. It's a space, right? It's like an actual. Could be like a 3D space or whatnot, right? One-dimensional manifolds are lines and circles, but not figure eights? What are figure eights? Because no neighborhood of their crossing points is homeomorphic to put in one space. Two-dimensional manifolds are also called surfaces. Ah, there you go. Okay. Examples include the plane and the sphere and the torus, which can be embedded in three-dimensional real space, but also the Klein bottle and real projective plane, which will always self-intersect when immersed in three-dimensional space. Yeah, okay, so this is really like an abstraction of just space, right? So we can still think of it as a space of some kind that is reached in the limit of a system with a sufficiently large number of states. And in particular, we can imagine finding a given foliation defining coordinates of some kind on it that will denote whatever this is. So this means that within a foliation, any state that appears in the multi-way system can be assigned a position in this multi-way space. So you'd kind of give a position or coordinates to each of these elements. In the standard formalism of quantum mechanics, states are thought of as vectors in a Hilbert space, and now these vectors can be made explicit as corresponding to positions in multi-way space. Oh, look at these. These are these counting things, right? But now there's an additional issue. The multi-way system should represent not just all possible states, but also all possible paths leading to states. And this means that we must assign to states a way that reflects the number of possible paths that can lead to them. In effect, therefore, each branch-like hypersurface can be thought of as exposing some linear combination of basic states. Okay, yes, and that's the definition of the wave function, right? And that is actually what you would, yeah. So that's each of these foliations. The entire foliation is this system state. Each node is a basis state, represents a basis state. The fact that there are just A's and B's here, it's just a way to exemplify transformation. But you'd start in effect, each branch like comes as exponentially a combination of basic states in a way, yeah. Exactly. So let us say that we want to track what happens to some part of these branches. And I guess these correlations are also what you then see in density matrix, right? Probably that's the case. Because that's the idea, I think, of the off-diagonal elements of the density matrix. They represent the correlations between states. So that's not such a stupid idea. It's really cool, actually. Let us say that we want to track what happens to some part of this branch-like hypersurface. Each state undergoes updating events that are represented by edges in the multi-way graph. And in general, the paths followed in a multi-way graph can be thought of as geodesics in a multi-way space. What are geodesics? They use this word tons of times in the videos, and I have no idea what it is. It just in geometry, geodesic is commonly a curve representing, in some sense, the shortest path between 2 points, okay, in a surface. So, in a multi-way space, in general, the paths followed in the multi-way graph can be thought of as geodesics in a multi-way space. So this multi-way space really does not just hold the quantum state, but like the evolution of the quantum system. And to determine what happens to some part of the branch-like hypersurface, we must then follow a bundle of geodesics. A notable feature of the multi-way graph is the presence of branching and merging, and this will cause our bundle of geodesics to diverge and converge. Often in standard quantum formalism, we are interested in the projection of one state on another. In our setup, the only truly meaningful computation is of the propagation of a geodesic bundle. But as an approximation to these, that should be satisfactory in an appropriate limit. We can use distance between states in multi-way space and computing these terms. What? But as an approximation to these that should be satisfactory and the appropriate limit, we can use distance between states in multi-way space. And computing these in terms of the vectors, the expected Hilbert space norm. What is the Hilbert space norm? Oh, there's an actual, it's in German, it's von Neumann. Oh, mathematical foundations of quantum mechanics, that sounds scary. What did I open here? Hilbert space, whatever. What is the Hilbert space norm? Time evolution on our system is effectively the propagation of geodesics through the multiplied graph, and to work out a transition amplitude between initial and final states, we need to see what happens to a bundle of geodesics that correspond to initial state as they propagate through the multiplied graph. We know to measure essentially cross-sectional areas. Give me a second, I'll be right back. So, is this working again? Yeah. And in particular, we want to know the measure, or essentially cross-sectional area of the geodesic bundle when it intersects the partial hypersurface defined by a certain quantum observation frame. What is a quantum observation frame to detect the final state? So there's a bunch of concepts here that I'm not really quantum reference frame. I guess that's what we checked at the very beginning, I think 2 sessions ago, which is about the measurement stuff. To analyze this, we consider a single path in the multiway system corresponding to a single geodesic. The critical observation is that this path effectively turned in multiway space every time a branching event occurs, essentially just like in the simple example below. If we think of the turns as being through an angle theta, the way the trajectory projects into the final branch-like hypersurface can be represented by what? By to work out the angle theta for a given path, we need to know how much branching there will be in the region of the multiway graph through a piece through which it passes. Whoa, 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 whoa. Okay, so these starts to get a bit messy, right? Because now there's some sort of geometrical mapping to these being a surface, and now we're talking about angles. The way the trajectory projects onto the final branch-like hypersurface. So I guess these, what, projecting to what? But now recall I'm these IKEA I got totally lost, so I think I'll have to just redo that next time. What is this angle theta? I don't know. But now recall that in discussing spacetime, we identified the flux of edges through space-like surfaces, and the causal graph is potentially correspond to energy. Ooh, okay, so I might have to go look that up. And the space-time causal graph, however, is just a projection of the full multi-way causal graph in which branch-like directions have been reduced out in a causal invariant system. It does not matter what direction this projection is done. This is wow, that jumped too much ahead. But now, suppose that in the full motor, the flux of edges across space can still be considered to respond to energy. To energy, the flux of edges across space like cyber. What the heck? Now note that every node in the multi-way causal graph represents some event in the multi-way graph. Every node in the multi-way causal graph. But events are produce branching and turns. Yeah, so the branching are the turns of these geodesics. So what this suggests is that the amount of turning of a path in the multi-way graph should be proportional to the energy multiplied by the number of steps, or effectively the time. In Instagram formalism, energy is identified with Hamilton H. So what this says is that in our models, we can expect transition amplitudes to have the basic form in agreement with the result from quantum mechanics. So I think what this is trying to say is that what this is trying to say is that in a way you can describe these geodesics as, like, in a way, the shape, the geometrical shape and maybe direction of these geodesics or their projections, I don't know, the D shape is something that is then corresponding to energy, which is at the end of the day what the Hamiltonian is there for, right? It's telling you how the energy of a system is evolving. So here we start touching some interesting points, which I'll have to definitely dig into. So energy and evolution, transition amplitudes. I've never come across this term before. The transition amplitude in most commonly used operator approach, the transition amplitude expresses the vacuum expectation value of the product of particle creation and heat. What? Oh, cool. Learned something new. Transition amplitude with transition probability. In quantum mechanics, the physical system corresponds to a Hilbert space. States correspond to not in a one-to-one way to points in Hilbert space. And the physical postulate is that the transition amplitude, a complex number, from a state corresponding to V into state corresponding to U, is given by where the physical meaning of the transition amplitude is that if you take the square absolute value of these complex numbers, you get the actual probability of the system going from the state corresponding U. Oh, so this is a whole new thing. I was not aware of that there's also transition probabilities. So there's also the concept of the probability of a state evolving into another state, which I guess is then related to an operator. Or is it that that's the operator? It's got to do with some operator, right? So we're learning something new, transition amplitudes. In agreement, like, yeah, that would be the Hamiltonian. That's kind of like the operator that encodes the evolution, I guess. Yeah, okay. But there's a lot of stuff to unpack in here. And I'll probably want to reread these next time. To think about this data, we need not just single energy quantity correspond to an overall rate of events, but rather we want a local measure of event rate as a function of location in multi-way space. In addition, if we want to compute in a relativistically invariant way, we do not just want a flux of causal edges through space like hypersurfaces in some specific foliation, but now we can make a potential identification with standard quantum formalism. Okay. This sounds like what comes next is important. We suppose that the Lagrangian density No idea what that means. Corresponds to the total flux in all directions, or in other words, the divergence of causal edges at each point in a multi-way space. What is Lagrangian density? Oh, that actually is a link. So that is that's a link to Wikipedia. Field theory, God. Lagrangian field theory is a formalism in classical field theory. Lagrangian density. The Lagrangian density. Who's these though? So in classical mechanics, one usually considers Lagrangian as L equals K minus U, where K is the kinetic energy and U is the potential energy. One lets the Euler-Lagrange equations and everything is fine. One thing is, oh, okay, if we're in a system, we can apply the kinetic energy and potential energy for Lagrangian for it. The point is that I've already seen a different object, the Lagrangian density, which is on the other hand a full form on space-time. The main difference being that the action is the integral of L over time, and the integral of whatever this is all over all space. The hell? That is really uncharted territory for me. What is the Lagrangian density? Corresponds to total flux, blah blah, to path motors going through water space. To know how much turning to expect in the path, we need in effect to integrate the Lagrangian density along the path, together with the appropriate volume element. This will give us something of the form e to the power of is, where s is the action. But this is exactly what we see in the standard path integral formulation of quantum mechanics. What is the path integral formulation of quantum mechanics? Wow. Idea. The notion of path integral originates in and is mainly used in the context of quantum mechanics, quantum field theory, where it is certain operation supposed to model the notion of quantization. The idea is that the quantum propagator, the functor, what is a functor? Oh God. Oh God, that's too much. That's definitely too much. There are many additional details, but the correspondence between our models and the result of standard quantum formalism is notable. That's all I could take as well from this, I guess. So, ran out of coffee. It is worth noting, pointing that our model, something like the Lagrange, that in our model, the Lagrangian is ultimately not something that is just inserted from the outside. Instead, it must emerge from actual rules operating on hypergraphs. In the standard formalism of quantum field theory, the Lagrangian is stated in terms of quantum field operators, and the implication is therefore that the structure of the Lagrangian must somehow emerge as kind of a limit of the underlying discrete system, perhaps a bit like. Okay, so this Lagrangian thing is important. One feature of standard kind of formalism is the appearance of complex numbers for amplitudes. Yeah, indeed. Here the core concept is the turning of a path in multi-way space. The complex numbers arise only as a convenient way to represent the path and understand its projections, but there is an additional way complex numbers can arise. Which is a metric on the full space of the graph, the normal convention for, okay, so this is, yeah. Okay, so following, let's try to recap a little bit. So following the typical way this kind of documentation seems to be laid out, right? It's like we try to map things to this model. And in the quantum formalism part, so the first half is quite digestible. It's about like mapping states to nodes and what each foliation means. And then, so there is a part of these that is about the states, and then there's a part of these that is about the evolution, which is the whole multi-way. I gotta get more used to the proper labeling of these things, right? So the multi-way, that's the multi-way graph, right? And so that represents how the system evolves. Yeah, so basically that represents how the system evolves. Now, this evolution is something that apparently it's also well studied and defined in quantum mechanics, right? That's how, so you have the whole Schrodinger equation, I guess, that tells you how things evolve. And then and that there you have this Hamiltonian thing of a system that tells you how the energy changes. And this somehow tells you how things evolve. And so what they're saying here is that this is represented by the paths, and that you can actually have then, of course, some sort of study of these paths. They call them geodesics, because then the idea is you get that graph-like, because that's kind of like, it's not a hypergraph, that's like a graph-like thing. Um, that's kind of like a graph-like thing, and you make that a monoid, or you understand that as a surface, and then you study how these paths look like geometrically speaking in this space, and the way these paths, so these paths are going to have turns. That's what they say, right? Because yeah, basically that's kind of like the graph is growing and shrinking and whatnot, right? It's not like a straight line. So they're going to have turnings, and then these turnings are then somewhat related to the energy of the system. I think I kind of, sort of the really, really high level picture is there, but it's not yet fully, it's proportional to the energy multiplied by a number of steps, or effectively the time. I don't know how they just derive these things like these. And then there's this Lagrangian stuff here popping up. But here I think I need to, just if I would like to just scratch, just to kind of like, take a little bit of a look under the hood on, what this Lagrangian thing is, because this has been popping up often, and it's got a relationship to classical mechanics and then Lagrangian mechanics and whatever. We need to integrate the Lagrangian density. No matter how much turning to expect in the path, we need in effect to integrate the Lagrangian density along the path. So how would you know how much turning to expect in the path? You're here and you know how much turning you're going to expect in this path for looking forward. So it's what they're saying is it's a function of the flux, and by flux maybe I understand sort of the something that describes all these geodesics passing through that specific point, and that tells you how much turning you can expect, I guess. So that's why they make a correspondence between the Lagrangian and the flux. Divergence of causal edges. What was a causal edge again? Is this a causal edge? Are these causal edges? Are these causal edges? Multi-way space. Because this multi-way causal graph is something else, right? Multi-way causal graph. Wasn't these I think that's the multi-way causal graph, I think. I probably have to go back to the basic concepts, right? For that, I'm guessing. Um, and then the flux of causal edges. And that's somewhat like this Lagrangian stuff. And that tells you the turning, yeah, and somewhat that. So, but I get it. So this part kind of talks about the two different things. Oh, wait a second. Why is it telling you that OBS is going to get shut down? No, I don't want to exit. There you go. Cool. So, um, so these talks about two things, and that seems to be then a good enough of a framework, right? So we're talking about states, and we're talking about these foliations, and we're talking about these different, like how the correlations of the states look like, and I think that's what they call entanglement here, which is kind of a bit misleading because I've always thought about entanglement as a property of the full state itself, not as a property of the different states. And the different states are correlated; they are correlations, right? Um, I mean, correlations is kind of like the relative phases, I think. But these are correlations. Yeah, I think so. I think they are because I think the off-diagonal elements of the density matrix, that's what they are, right? Uh, Non-zero off-diagonal elements of the density matrix signify that these features a quantum superposition between the elements of the bases that you choose to represent. Yeah, coexisting. Yeah, yeah. Okay, but there's the whole thing of the system in a snapshot and then the evolution. And what there's something new to explore here is this whole Lagrangian stuff, then the whole Hamiltonian stuff. And then there's also these, how they call that? The transition amplitudes. These I was not aware of, that there's such thing either. Okay, that was useful. I should probably take some notes, but I really don't know how to structure these notes. I'm kind of a bit of a lazy guy with this stuff. I think if I forget, then I forget, you know. But yeah, cool. No, I think that was again, a bit messy, but I think it was useful. See you next time.